Assalamu alaikum everybody. This is the third lecture of the basic electronic course. I'm Dr. Saad Ahmad. Today we will be discussing about we will be discussing about the type of semiconductors, and there are two types basically, the intrinsic semiconductor and the extrinsic semiconductor. We'll discuss in detail how these semiconductors are formed and how they are applied and used in electronic circuits for making electronic devices. Okay, in the last lecture we discussed about different type of materials, the conductors, the insulators, and the semiconductors, and our main topic is semiconductors, which have four valence electrons, and they belong to group 4 in the periodic table. You can go and check it out. And the thing is that these materials, as I have mentioned in the earlier lecture, that they behave as insulators when used in normal temperatures, at room temperature. So this means that you cannot use them as it is for electronic purposes. So what you need to do is to convert it, mix it with other materials, and then make it usable for electronics. This is the diagram, the structure of atom of silicon, where you can see there are 14 protons present in the nucleus and 14 electrons revolving around the nucleus. We are interested in the last orbit, or the valence orbit, and the valence orbit is the one which basically describe the characteristic of a material for electron, is it usable for electronics or not. Anyway, so what we are going to do is that we will be using a relative figure, and we will be showing the structure with not all the 14 electrons. For the semiconductor we will be only showing the 4 electrons and the nucleus, to make our diagrams simple to understand. But this is true that all the 14 electrons in the case of silicon are present in that diagram, so that is understood. For simplicity we will be using it with only 4 valence electrons, because those are the electrons which we are interested in. Anyway, let's continue. Okay, let's look at this figure, where there is a nucleus with Si written on it, that shows that nucleus, and the shaded area is showing that it includes the nucleus as well as the remaining 10 electrons of the silicon atom inside this, and the remaining 4 electrons, which are the valence electrons, are shown in the figure. This is the diagram which we'll be using to move forward from now on. But it is a silicon atom and it has 14 electrons in it. Okay, so let's go further. There is a process called crystallization. Okay, before going to the silicon clusters, or the crystal structure, we'll just go quickly to this example where we can see that there is a question: what is the net charge of a silicon atom if it loses one of its valence electrons, if it gains an extra electron in the valence orbit? What happens if it loses one of its valence electrons due to any force or any potential difference, if that electron dislodges from the valence orbit? So the answer is if it loses an electron, it becomes a positive ion with a charge of +1, and similarly if it gains an electron, it becomes a negative ion. So this is the thing which you need to focus. These are the two points. If it loses, it becomes positive ion. If it gets an extra electron, it becomes negative ion. Okay, so that's it. Now moving forward, we will discuss now the silicon crystal. As mentioned earlier, when silicon atoms combine to form a solid, they arrange themselves into an orderly pattern that is called crystal. They, when a silicon atom combines to form a solid, they arrange themselves into an orderly pattern called crystal. Each silicon atom shares its electron with the four neighboring atoms in a way as to have 8 valence electrons in its valence orbit. Remember what a material becomes if it has 8 valence electrons in the valence orbit? Well, I guess you know it. It becomes insulator. That is why when there is a silicon crystal, it behaves as insulator because all the valence orbits have now 8 electrons. I'm going to show you the diagram. Okay, look at this diagram. We can see that the electrons focus on the central atom, this one. Okay, so you can count the electrons in this orbit, and there are 8. 1 2 3 4 5 6 7 8. So 8 electrons. But the thing is that one electron belongs from this is from the second electron, this is from the third atom, and this is the fourth atom. So these are the 4 atoms which are contributing an electron and sharing an electron with the central atom. These are all silicon atoms, having each one of it having 4 valence electrons, but when they are forming a bonding with the central atom, that is a covalent bond where sharing of electrons take place. You must have studied this in your school and college chemistry. So these electrons are coming from the neighboring atoms, and 4 electrons, this one maybe, and this one, and this one. These 4 electrons belong to the central atom. So if you count them all together, because they are all now, after the bonding process, they are all now in the valence orbit. So they are 8 now, and 8 is chemically stable, which makes it stable, and when it is stable, it is not going to allow electrons or current to flow through it in the normal conditions. And if you stretch this diagram, add more atoms on up and down, you can see to form the crystal with maybe 10 atoms, 20 atoms, and you point your finger to any atom and count its valence electrons after the covalent bonding, you will find that it is carrying 8 electrons. That is why semiconductors are useless for electronics purposes when they are in pure form. So pure semiconductor is not usable for and not good for us for electronics. Okay, so what happens is that there is a process known as a doping process, and if you want you can write it down also, that doping process is the process of adding impurity atoms to a pure semiconductor material. and by doing this we basically convert the pure semiconductor, which is also known as intrinsic semiconductor, into impure, and that is extrinsic. See, so after the doping process, the semiconductor formed is called extrinsic semiconductor. Pure semiconductor, as we know now, cannot be used for electronics. Impure semiconductor, after adding of impurity atom through the doping process, we have a new semiconductor formed called extrinsic semiconductor. Okay, so okay, this is the periodic table. You must have seen it before, but today we are looking at the group 4 elements, and those elements are, starting from the top, you can see carbon, silicon, germanium, tin, lead, and fermium, flavorium. So carbon has six electrons, or the atomic number of carbon is 6, that means it has 6 electrons. Silicon 14, germanium 32, tin 50, lead 82. If you draw the diagram, atomic structure of these elements, you will find all of them has 4 electrons in the valence orbit, and the two marked in between, that is silicon and germanium with 14 and 32 atomic number, is the most widely used for electronics. So we normally use these two material. You will find 90% of the devices are made using the silicon, and about 10% or less maybe germanium. Initially, when electronics was introduced and there was a lot of research going on, initially germanium was the material of choice, but after some period of time it was found that silicon is a better choice for making devices. Anyway, still we use germanium material for some devices which are available in market. Anyway, we were discussing about the doping process. So what we are going to do now, we wanted to add an impurity atom from these available elements in the periodic table, and the most suitable ones are the one which belongs in group 3 and group 5. When you use group 3 elements, which are boron, aluminum, gallium, indium, thallium, these elements, if you draw the atomic structure of these elements, you will see that the valence orbit will carry 3 electrons, and that is why they are also known as trivalent elements. If you look at the group 5 elements with nitrogen, phosphorus, arsenic, antimony, bismuth, so on, these elements, if you draw their structure according to their atomic number, you will find that they are having 5 valence electrons, and that makes them known as pentavalent atoms. So for doping process, the most suitable elements are group 3 elements like boron, aluminum, and group 5 elements like arsenic and phosphorus. So this was the thing which I wanted you to look at it, and I also want you to try and draw atomic structure of these to have a little deeper knowledge. And understanding of the topic. Anyway, so what we are going to do now is we are going to go back to this doping, and we can see that after doping process, when you use group 3 elements, the semiconductor formed will be called p-type semiconductor, and group 5 elements will, if you use group 5 elements as an impurity atom for doping purposes, it will make n-type semiconductor. So after doping process, there can be two type of semiconductors: the n-type semiconductor made when pentavalent impurities are used, and p-type semiconductor when trivalent impurities are used. Okay. So intrinsic semiconductors are, as I said earlier, are pure semiconductors like germanium, pure silicon, and at room temperature the number of electron equals the number of holes. And if we look at the extrinsic semiconductors, their characteristics are, if you look at the extrinsic semiconductor, when we add an impurity to pure semiconductor to increase the charge carriers, then it becomes an extrinsic semiconductor. Or if you perform the doping process, it becomes extrinsic. And doping process, as you know, is adding of impurity atoms to the pure semiconductor. By doing this, we basically increase the number of charge carriers. Charge carriers, what are charge carriers? We are going to discuss in a short while. So these are basically the target of increasing the charge carriers by using the doping process, making extrinsic semiconductors, and so on. Okay, we need to understand two things here, that electrons are represented by negative, and there is also one thing which is called hole, and it is a positive charge. So remember, we have discussed earlier about the charge carriers. So these are the charge carriers. Charge carriers can be hole, can be electrons. And if you look at a piece of semiconductor, this is a piece of semiconductor, and if it is connected to a battery, if you connect this to a battery, you will see that electrons will start, this is positive terminal, this is negative terminal, and electrons will start moving from negative to positive, flows through this and will be attracted by the positive terminal and complete the circuit. This is the basic flow of electrons. But when you talk about semiconductors, the story is a little different, and we have two type of charge carrier. One is electron and the other one is hole, and we are going to discuss further about it. Okay, let's see, this is a silicon atom, and it has been shown here as these four electrons are shown here, which are in the valence orbit, and for due to any kind of pressure applied on this atom, there is a possibility this any one of these electron may be dislodged from this orbit and moves on and moves further. What remains is here is a positive space, a vacant space which carries a positive charge. because initially this atom was neutral because number of electrons and number of protons were same, but when this electron leaves the orbit, it makes this silicon atom positive ion as discussed earlier, and this hole which is positively charged will be there, and if for any reason any other electron comes near it may go into it and occupy this space. This is the process which happens continuously inside these semiconductors. The force can be voltage, or it can also be heat, that is temperature. If you increase temperature, if you okay, look at this electron. If for any applied voltage, if this electrons dislodges from this place and moves forward onward, it is going to create a vacant space in the orbit. We consider this vacant space as positive charge, and we call it hole. So we have two terms here, as I discussed earlier: electron and hole. Electrons are negative charge carriers, and this hole created by the absence or moving away of this electron is called hole, and it is positively charged. And this can happen for many reasons. One could be the voltage which is applied on this material, or it can be because of heat, that is increase in temperature. If temperature increases, the material start vibrating, and due to that vibration, molecular level vibration, the electrons can dislodge from the orbit and moves away. Similarly, what can also happen is, if a electron other electron comes in vicinity of this positive charge hole, you know that unlike charges attract each other, so this will be attracted and will occupy this vacant space, and complete the orbit. So you see, this process continuously happens inside semiconductors. We cannot see it, but through this diagram we can visualize it. Okay, the ambient temperature, few terms which I want you to understand and remember. The ambient temperature is the temperature of the surrounding air, which is absolute zero, that is minus 273 degrees. Anyway, what I have discussed in the previous diagram, that when the temperature increases, the mechanical vibrations at the atomic level also become stronger. When you pick up a warm object, the warmth you feel is the effect of vibrating atoms. So in a silicon crystal, this vibration can dislodge an electron from the valence orbit, and when this happens, the electron goes away from the orbit, leaving a space behind, and that electron is called free electron. And this departure of electron creates a vacancy in the valence orbit, which we call hole, and we consider it positively charged. Okay. The hole will attract and capture any electron in the immediate vicinity, as I discussed earlier. The existence of electrons, and holes. The existence of hole is this critical difference between conductors and semiconductors, and holes enable semiconductor to do all kind of things that are impossible with conductors. So that this is hole, and you just need to remember that holes are positive charge carrier and electrons are negative charge carrier. Moving forward, in a pure silicon crystal, the thermal energy creates an equal number of free electrons and holes. How is that? Simple. If you look at this diagram on the left side of the screen, you can see that this electron has moved away and left this space. So when one electron leaves, it creates one hole. That is why the number of holes and number of electrons will be equal when thermal energy creates vibration. The free electron moves randomly throughout the crystal. Occasionally, a free electron will approach a hole, feel its attraction and fall into it. This is called recombination. So, the process here is that we have two things here. One is that during the life cycle, some free electrons and holes are being created by thermal energy. Other free electrons and holes are recombining because there are millions and millions of electrons and holes. So some are being created by thermal energy, some are recombining, and some electrons and holes exist temporarily awaiting recombination, means they are moving somewhere randomly in the crystal. I want to show you another diagram. See this diagram, this is the recombination thing. The electron falls back into this anyway. So one more term here, the amount of time between the creation and disappearance of a free electron is called lifetime, and it varies from few nanoseconds to several microseconds depending upon how perfect the crystal is. This means that this is a very quick process, but it happens, and these are the few processes which we need to know how they work if you want to understand the working of different semiconductor devices. Okay, that is it for today, and we will continue our discussion in the next lecture. If you have any questions, you can contact me and ask questions, and make sure you read your book so that you understand better. Thank you very much, and Allah Hafiz.